Let's spend a couple of minutes talking about friction here. We already addressed friction, talked about the two types of friction, static and kinetic friction. Definition of static friction, we already gave you this, right? When we gave you the last set of notes on types of forces. It's the force of friction that prevents an object from beginning to move. The force that acts on an object that's at rest, that tries to keep it from starting to move. But the force of static friction is a wacky force. It really is. Because it changes. It's not the same every time you push on something. If I push on Leah's desk with a force of 10 newtons, static friction is one value. If I push on Leah's desk with a force of 20 newtons, static friction is a different value. Static friction has a value only of what it needs to be. If it only needs to be 10 newtons, it's only going to be 10. If it only needs to be 20, it's only going to be 20. Static friction changes with how hard I push. It varies with the applied force. There is a maximum value of static friction that can act between any two surfaces. And the force of static friction will be however hard I push on the object unless I exceed the maximum value. So for instance, if the maximum value of static friction between Leah's desk and the floor was 30 newtons, okay, remember that. 30 newtons is the maximum possible force of static friction. If I push on Leah's desk with a force of 10 newtons, then static friction isn't 30, it's only 10. If I push on Leah's desk with a force of 20 newtons, static friction isn't 30, it's 20. If I push on Leah's desk with a force of 29 newtons, static friction is 29 newtons. If I push on Leah's desk with a force of 31 newtons, what happens? Well, the maximum static friction was 30. What happens? The desk now moves, right? If I push on it with a force that's higher than the maximum force of static friction, the desk will move. So, however hard I push is equal to the value of static friction, unless I push harder than the maximum possible value. And then the desk moves, and now we don't have static friction, now we have kinetic friction. So maximum value between Leah's desk and the ground was 30 newtons. I push with 10, static friction is 10. I push with 20, static friction is 20. I push with 29, static friction is 29. I push with 31, I've exceeded it, now it moves, static friction is 0. Now kinetic friction kicks in. So a wonky force we got here. A force that changes, seems to know how hard I'm pushing. And it's one of those kind of lazy forces. It only does what it needs to do. It's kind of like some students, right? Some students work really, really hard, do really, really well, get 98% in physics 20 or 98% in chemistry or whatever the case may be, because they work really, really hard. And then there's some students that don't do anything. They're just really, really lazy. But then there's some students that they work, but they work only as hard as they need to work. Static friction is kind of like those students. It works, it does what it needs to do, but nothing more. Okay, if it only needs to be 10 newtons, it's only going to be 10 newtons. If it only needs to be 29, it's only going to be 29. It only does what it needs to do. Kinetic friction, on the other hand, also known as dynamic friction, we've already defined as the force of friction that acts against an already moving object, that resists the motion of the object that is already moving. Good thing about kinetic friction is that it is what it is. Kinetic friction on Leah's desk is 20 newtons when the desk is moving. It doesn't matter how fast the desk is moving. It doesn't matter how hard I push it. If the force of kinetic friction is 20 newtons, then the force of kinetic friction will always be 20 newtons. It's not a changing force like static friction. It's not one of those forces that only does what it needs to do, like static friction. If kinetic friction can be 20 newtons, then that's what it's going to be all the time. It's a consistent force. This one's our lazy force. This one's our consistent force. Now here's the thing. The force of kinetic friction would normally be lower than the maximum force of static friction. What does that mean? Well, it means that if I push Leah's desk And the maximum force of static friction was 30 newtons. I push it with 29 newtons, static friction would be 29. I push it with 31, the desk moves. Static friction is 0, kinetic friction kicks in, and the value of kinetic friction would be somewhere in the range of maybe 20. It's less, not always less than static friction, but less than the maximum value of static friction. You guys have experienced this. All of you have. You go to push something. You ever notice this? You go to push something heavy. It's so hard to get moving. It's so hard to overcome the friction that acts between the ground and that heavy object. But once you get it moving, you find it's easier to keep it moving. You ever notice that? You're pushing a heavy box. It's hard to get it moving. You got to move it. Ooh, and now it's easier. You don't want to stop it. You don't want to stop it because you know it's going to be difficult to get it moving again. Once it's moving, it's easier. That's because the force of kinetic friction that resists the motion is lower than the maximum force of static friction that you had to overcome. Does that make sense? Here's one for you. When I was your age, learning to drive, cars that were just coming out, some of them had what's called anti-lock brakes. Some of them didn't have anti-lock brakes. Anti-lock brakes are brakes that pump. The brakes are automatically pumped by a computer in the event of skidding. And that helps you to stay on the road, and it helps you to stay in control. When I was taught to drive, a lot of cars didn't have anti-lock brakes. It was only the fancy cars that had anti-lock brakes. I was taught, when I learned to drive, that if I was ever on a patch of ice and sliding on a patch of ice, to not put your foot on the brake and hold it there, but to pump the brakes. Okay, pump the brakes on and off. Now you don't have to do that because anti-lock brakes do that for you way more effectively than you could ever do it yourself. Why does pumping the brakes keep you in control when you're sliding on ice better than just slamming your foot on the brake and keeping it there? Well, when I slam on the brake, I slide, right? The brakes lock and the tires slide. What kind of friction is that? What kind of friction is that when the tires slide on the ice? Kinetic friction. All right, so you got friction. You got kinetic friction acting between the tires and the ice. Not enough, though, because you're having a difficult time controlling it, right? But there is some friction there. When you pump the brakes, or when anti-lock brakes pump the brakes, what it does is keeps the brakes from locking. In other words, the wheel is always turning. 1 second. The wheel is always turning, which, believe it or not, is a good thing. Here's your wheel. Take a look at this one spot. The UPC symbol on this bottle is going to represent one spot on the wheel. As that wheel is always turning, notice it's not sliding. It's not sliding on the ice. Okay, it's not moving relative to the ice. Right now it's not on the ice, comes down, oh, it's touching the ice. Okay, it's not moving on the ice, it's stationary on the ice. So in other words, as the wheels keep moving, ironically, it's static friction that acts between the wheel and the road. Which one's bigger, static or kinetic? Static friction. That's why it's better to keep your wheels moving on the ice than it is to have your wheels locked up on the ice, because static friction is bigger than kinetic friction. It's easier to control with bigger friction, right? All right, that's it for today, guys. We'll pick up there with a little bit of mathematics tomorrow on this, okay?